Hello, everyone. In the previous video, we introduced parametric curves. These are paths or curves through the Euclidean plane, the XY plane that we all know and are used to, determined or defined in terms of a sort of hidden parameter. In our case, it was t, typically representing time, as we saw with our examples. Now, this is a calculus course, and so of course, we want to know how to do calculus using these curves. And that's what we're going to focus on for the next few lectures. And in particular, what we'll talk about today is finding tangents, so tangent lines at a single point on the curve, for example, and how we can find areas defined or areas of shapes determined and defined and outlined in terms of these parametric curves. So let's go ahead and let's jump right into this. So the first thing that we want to be able to do is if we have some, say, general parametric curve, and we know that points on the curve, x and y, are given in terms of, say, functions, f of t and g of t, we would like to know what the derivative is of the curve of y in terms of x. Okay, so clearly we can get the derivative of y in terms of t. This is just g prime of t, as long as it works, as long as you can take derivatives here. Similarly, you can get the derivative of x in terms of t as f prime of t. But like I said, t is sort of hidden in the background. It's a background variable and it might not be useful to us. We might want to ask ourselves, what is the rate of change of this function from y in terms of x? Similarly, we might ask ourselves, what is the slope of the tangent line right here along the function? Well, in that case, then we're going to require dy dx. So the usual derivative that you're used to, y in terms of x. Well, how do we do this? Well, first of all, we can use the chain rule to see that if you take the derivative of y with respect to t, this is the same as taking the derivative of y with respect to x, and then x with respect to t. If you're having trouble seeing this, sometimes it helps, especially in this case, to sort of treat these things as fractions. I know that you learn calculus early on, and your teachers always say, don't look at these things like fractions. They're not fractions. But of course, with Leibniz rule and with the chain rule, these things are best understood using fractions, right? Because you can see the sort of dx's canceling here. But what this really tells you is that if you want to know the rate of change of y with respect to x, dy dx, this is the derivative of y with respect to t divided by the derivative of x with respect to t, which, again, if this is a parametric curve, this should be accessible to us because it's g prime over f prime of t. Now, there are, of course, nuances that come with this that we're going to sweep under the rug, but of course we need to be able to divide by the derivative of x with respect to t, so it has to be non-zero, and every time we take derivatives, we have to ask ourselves, does the derivative actually exist? So we're going to sort of sweep that under the rug for the time being. We don't have to think about it. Just think about this as a purely formal experiment here. Okay, so then how do we do this in practice? Let's take a look at an example. So let's say find the tangent curve, or find the tangent to the curve. And our parametric curve is x is equal to secant of t, and y is equal to the tangent of t, where minus pi over 2 is less than or equal to t. It has to be strictly less than because of the domain of secant. So just in case you're wondering why I don't have less than or equals there. And we're going to do this at the point square root of 2, 1, where t is equal to pi over 4. Okay, So how do we do this? This is sort of an old school original calculus question that you would have got when you first learned derivatives, maybe not using these parametric curves, but it's the same principle, right? Once you calculate the derivative of y with respect to x, you have the slope of your tangent line. And then with that slope of that tangent line, you can just calculate the tangent line knowing that it goes to the point square root of 2, 1. So of course, most of the work comes from finding the derivative. But from our formula above, dy dx, this thing is the derivative of y with respect to t divided by the derivative of x with respect to t. And so in this case, we get the derivative of tan, which is secant squared of t, divided by the derivative of secant, which is secant of t times tan of t. So I'm just taking derivatives of the x and y components with respect to t. We can cancel out one of those secants, and we get secant of t divided by tan of t. There's no point in simplifying this a little further in terms of sines and cosines. It's totally fine with us. Now, the point is, I can find the slope of the tangent line by just plugging in the value of t into dy dx. So at t is equal to pi over 4, we get dy dx at t equal to pi over 4 is equal to the secant of pi over 4 divided by the tangent of pi over 4. Now, secant of pi over 4 is equal to square root of 2 over 1. And the tangent of pi over 4 is 1. So the slope of this thing is pi over 2. And so that tells us that the tangent line, well, this thing is equal to, so you set this up, y minus b, in our case, b is 1, is equal to the slope, square root of 2, and then x minus a. A is the square root of 2. So I'm just going to put some little notes here. This is the slope. This is x component we know. That's given to us, right? We go through the point root 2, comma 1, and this is the y component we know. And so you can rearrange this if you'd like to, and this will tell you y is equal to the square root of 2 and then minus 1. So that is the tangent line. Now, in terms of what we talked about in the last lecture, maybe it might be a good exercise for you to try and figure out what this curve looks like. And in fact, we did this curve in the last lecture. It's just dressed up in a different way. So notice that if you take the x component squared and you subtract the y component squared, this is secant squared minus tan squared. And there's that Pythagorean trigonometric identity in terms of secant and tan that tells us this thing is equal to 1. And so this implies we're on, or the curve, sorry, is a hyperbola. The curve is a hyperbola. In fact, with t between minus pi over 2 and pi over 2, the x component is positive, so it's literally the exact same hyperbola that we looked at in the last video lecture. And so if you need to go back to that, take a look at it, try and compare back and forth. And this goes to what we concluded with, or one of our last examples in the previous video, where you can dress up these curves in different disguises and still arrive at the same curve. Okay, so now let's ask ourselves how we can compute the second derivative of a function. Well, let's set y prime just as a placeholder equal to dy by dx, which we calculated from the previous example. And so using, again, the the rule that we had, the chain rule, we get dy prime by dt is equal to dy prime dx times dx dt, which we can rearrange. We get dy prime dx is equal to dy prime dt. So we can take the derivative with respect to t here again, and then dx by dt. And just to simplify off the left-hand side, of course, d dx of y prime, that is just the second derivative of y with respect to x. So this gives us, again, a nice little formula for computing the second derivative of your function y as a function of x, or your second derivative with respect to x. And so let's take a look at another example here. So now that we have formulas, it's mostly just sort of a plug and play type thing. So let's find the second derivative of y with respect to x as a function of t if x is equal to t minus t squared, and let's say y is equal to t minus t cubed. Okay, so there's sort of like a three-step process here, right? The first step is finding the first derivative, so y prime. So y prime is equal to dy dx. That's sort of how we defined it above. And we know that dy dx is dy dt divided by dx dt, which these are relatively simple derivatives to compute now. We have 1 minus 3t squared divided by 1 minus 2t. And so now we can take the derivative of that thing with respect to t, because that's what we need in the top of the fraction to compute the second derivative here. And so this is going to be a quotient rule application, right? This is the derivative with respect to t of 1 minus 3t squared divided by 1 minus 2t. I'll leave the quotient rule to you to have a little bit of fun with. I'll just tell you what the solution comes out to be. So I get 2 minus 6t plus 6t squared, all divided by 1 minus 2t squared. So if you think of this sort of step 1, step 2, step 3 gives me the second derivative of y with respect to x. In this case, it's given by the derivative of y prime with respect to t divided by, again, the derivative of x with respect to t. And so this gives me just the quotient from above. So I'm just copying down what I have. And then in the denominator here is 1 minus 2t again. And so I can simplify this, 2 minus 6t plus 6t squared divided by 1 minus 2t cubed. And so this gives me the second derivative. And if you wanted to do the third derivative, you could just follow my lead here, and you can, you can figure out based on these little chain rule applications how to find it. But this is kind of a weird thing. This is probably something that we haven't seen before, right? And this is the idea that you have a hidden variable t in the background, and you can use that to parameterize not only x and y, but also the derivatives, right? We're parameterizing the derivative of y with respect to x in terms of t as well. We're parameterizing the derivative, the second derivative of y with respect to x in terms of that hidden variable t. So t is doing all the work in the background, but it's giving me all the results in the plane that I care about in the x and y variables. Okay, so let's take a look at another cool application of this. Going back to maybe where we started at the beginning of this class a little bit, and talking about finding enclosed areas. So we're going to be able to do integrals with these things too. So let's say find the area enclosed by, now these things are called asteroids. I will show you what I mean. So the asteroid here is given by x is equal to cos cubed of t, and y is equal to sine cubed of t. And in this case, you have 0 is less than or equal to t, which is less than or equal to 2 pi. Now, you could follow my lead for sketching out the circle in the previous example, and you could show that, say, x to the 2/3 plus y to the 2/3 is equal to 1, right? And so that is your actual curve. If you want to sort of throw this into Desmos maybe to see what it looks like, or whatever your favorite plotting software is. But let me just show you what this thing looks like. Let me sketch it out. So let's do your XY planes. X, Y. And basically what it is it looks like a deflated ball a little bit. So it kind of looks like this. So it has these extrema, and then like this, and then like this. So we call this thing an asteroid. Here is the area that we are interested in inside of this thing. So the question is, how do we find the area? Well, the area by symmetry of the whole thing is 4 times the area in the first quadrant. Okay, so let's just look at the first quadrant and figure out how much area is in the top right corner of this thing, and then just multiply it by 4. So let me start fresh over here. The area is equal to 4. And now if you look back at the first quadrant here, you're running from x equal to 0 all the way up to x equal to 1. So your bounds of integration are x from 0 to 1. You're finding the area under the curve y, right? So you're going up to the curve y for different values of x. And you're sweeping over x equal to 0 all the way up to x equal to 1. So that means your integral is from 0 to 1 of y dx, right? And so I'm using y as a placeholder for that curve. That's the top right branch of my asteroid. So now what do I do? Well, we do a little bit of substitution. So first of all, we know y is equal to sine cubed of t. And we also know x is equal to cos cubed of t, which tells me that if I take the derivative here, dx is equal to 3 cos cubed of t, and then, minus 3 cos cubed times sine of t, because I have my derivative of cos. But also, if you're going from 0 to 1, you're going to flip the bounds as well. So that negative is not going to enter into this because I want to flip my bounds back around. So this is the same as going, this is equal to 4 times the integral from 0 to pi over 2. So just a substitution. Sine cubed of t, that's a substitution for y, and then the substitution for dt, 3 cos cubed of t, cos squared, pardon me, cos squared. This should be cos squared as well here, right? Cos squared sine of t dt, pardon me, I had to kind of squeeze it in there. I'm very, very sorry for that. I know it's kind of ugly. But again, let me just reiterate, x is equal to 1. Let's put this in blue. So why did I get rid of the negative? X is equal to 1 implies that t is equal to 0, and x is equal to 0 implies that t is equal to pi over 2. So the bounds of integration, once you do the substitution, are actually from pi over 2 to 0. Of course, you want to flip this around. That means you can get rid of the negative coming from the dt substitution, okay? But now, now we're in terms of a trigonometric integral. So we have 0 to pi over 2, sine to the 4t. Actually, let's put the 3 out front as well. Let's put that as 12. That's 4 times 3, and then cos squared of t dt. Now, I hope you haven't forgotten some of your integration techniques, in particular these trigonometric integrals. We remember when we have even powers of sines, we are going to use double angle formulas here. So we get 12 and then 0 to pi over 2. And this is going to be substituting for sine squared. So we have 1 minus cos of 2t divided by 2 all squared. So sine to the 4 is sine squared squared. And then 1 plus cos of 2t divided by 2, which is just the cos squared double angle formula, right? So notice that inside of everything, I have 2t now, not just t. All right, let's have a little bit more fun here. Let's clean this up. The 2 in the denominator, let's use like green to point it out. The 2 here squares, and there's another 2. So I have division by 8, 12 over 8 here. This is the same as 3 over 2. Integral from 0 to pi over 2. Now let's expand out those brackets. 1 minus 2 cos 2t plus cos squared 2t. So that's expanding out the first bracket that was sine to the 4. And I'm left with 1 plus cos 2t sticking out on the end here. Let's multiply them together. All right, now it should be a very routine computation. You should be very, 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 very good at this stuff by now, I imagine. You're probably used to doing a lot of these integrals because we've turned this back into an integral of one variable, t, and it's really just a trigonometric integral. Okay, nonetheless, let's keep writing it out. 1. So if I expand out this whole multiplication and clean it up in one step, this is 1 minus cos of 2t minus cos squared of 2t plus cos cubed of 2t dt, which I'm going to break this up into components that I can solve with different methods. So the first one, 1 minus cos of 2t, that one can be just integrated straight up. And then 3 over 2, the integral from 0 to pi over 2 of, sorry, there's a minus out front on this thing, cos squared of 2t dt, and then 0 to pi over 2 of cos cubed of 2t dt. Okay, so the first one, you're going to get 3 over 2 and then t minus 1/2 sine of 2t. So that's just using a straight integration of that thing, nothing fancy. And then what you're going to have to do is a double angle formula for computing that cos squared integral, right? So we might remember this, hopefully remember this. And in that case, you're going to get cos of 4t. So I'm going to leave the details for you to try and figure out on your own. And here now we get minus 3 over 4. And then this becomes t plus 1 over 4 sine 2t. And then finally, we have that last one of cos cubed. Again, if you have to remind yourself, that's okay. You can go back and check the trigonometric substitution work here. I'm just going to tell you what it is. This might be good practice for you anyways. And this is, 3 over 4, pardon me. 3 over 4, and then sine of 2t, and then minus 1/3 sine cubed of 2t. And then the whole thing is running from 0 to pi over 2. I am very, very sorry that I was not able to fit that whole thing in. But again, this is a definite integral. Everything is running from 0 to pi over 2, which is now just a calculator problem. So I'll just tell you what this should be. But you get an area of 3 pi over 8. So this is kind of cool, right? Because this gives me an explicit way of finding areas determined in terms of parametric curves, or at least where the outline of these things are given in terms of parametric curves. Now, when we come back with the next few videos, we're going to talk about how you can compute arc length of these curves. So this is something that we talked about early on in the class. Now we're going to modernize it using parametric curves. And we're going to modernize a lot of the other techniques that we talked about. So for example, finding surfaces and volumes of revolution in terms of these curves as well. And you should be able to predict, based on that last example, we can take these parametric curves and we can put them into, we can set up integrals in terms of the y's and x's that were given. And then, it's a nice substitution to get ourselves in terms of t, where we can sort of repeat all of these nice processes that we've been developing over the duration of this class.